Good morning. This is the second lecture of analysis of trust. In the first lecture, we have discussed about some basic consideration of the analysis of trust. So actually, we have discussed what the trust structure is, and today is the second lecture, and we will go to the next step of the analysis of trust. But before going to the analysis part, one more thing that was left previous day, that is the stability part. What the actually the stability of trust structure actually means. So we will first discuss this aspect. Now, while we will consider external stability, first of all, we will consider external stability. Just looking at the structure or some just considering few basic things, we have to understand whether the uh, particular structure is externally stable or unstable. So that is very important while we are considering before doing the analysis part, because if our structure is unstable, if we can just looking at the structure, if we can see that it is unstable, so then there is no issue of analyzing the whole structure, because whatever the load may be, it will leads to a failure. So the structure is externally unstable if all of its reaction are concurrent or parallel. That is, what does it actually mean? Just to go through this particular example, take this example. What is in this example, at this particular joint we have hinged joint, and at this particular joint we have roller joint, and you can see the direction of the roller is vertical. So direction of the roller is vertical means we are allowing uh, movement in the vertical direction, and we are restricting movement in the horizontal direction. So as we are restricting movement in the horizontal direction, there will be only horizontal reaction at this particular point, at this roller joint. Now, if we consider this particular joint, that is the hinged joint, it do not allow horizontal movement, as well as it does not allow vertical movement as well. Both the horizontal and vertical movement has been restricted in this particular joint. So in that case, when both the movement in horizontal direction and vertical direction is restrained, so we will get only two reaction forces, one in the vertical direction and another in the horizontal direction. But we can will not get any moment here, because as hinged joint allow rotation, so rotation is allowed. So there will be no moment at this particular joint, as well as the case of the roller was. So in both the particular joint there will be no moment. There will be only, at this particular joint there will be only vertical and horizontal reaction, and at this particular joint there will be only horizontal reaction, because the roller support is this kind of roller support is providing or allowing movement in the vertical direction, so there will be no such reaction. And what in our, if we go through the first point, the structure is externally unstable if all of its reaction are concurrent or parallel. Means this is one reaction, this is one reaction, and this is one reaction. Three reaction forces are there. Now, first point, what is the first point saying? That if all the reactions are concurrent, concurrent means they are passing, if they pass through one single particular points. So you can see that in this particular figure, this this particular, let's take different color. This particular force is going through this line, this particular force is going through this line, this particular force is going through this line, and if we consider this one, this particular force is also going through this line. So as we can see that all the three forces are passing through one single point. Means this point, all the three forces, all the three reactive forces are passing through this particular point. That means they all are concurrent, or they may be parallel to each other. So in case of concurrent, when the reaction, all the reaction forces are concurrent, the structure will become unstable. So for the configuration is concerned, we so far we will consider the configuration, structural configuration. Now, uh, but if we don't know this particular theory, that if all the reaction forces are concurrent, then only the structure is unstable. Let us assume we don't know that logic. So why, even if we don't know that logic, we can easily say just by visualization that, uh, just look at this particular scenario. What happened? The force is the reaction force at this particular point is like this, so they are restricting this too. Now at this particular joint, this particular support, there is no vertical restriction. So if we apply load at this particular point, if we apply load at this particular point, suppose let me apply some sorts of load, what will happen? Let me apply some load at this particular point. If we apply load at this particular point, the structure will automatically go down, because there is no such restriction. As there is no such restriction, the structure will automatically, this particular support is will automatically go in the downward direction. It cannot resist any single load, even a small load. It cannot just simply it cannot support. Even the dead load may be even if there is some load, if we consider dead load, then also the structure will fail to show certain the required strength. So even by just looking at the whole structure, you can see that this structure is unstable. And that is also theoretically we can say that if all the reactions are concurrent or parallel to each other, in this particular cases, all the forces, reaction forces, as you can see, they are parallel to each other. So all the joints are roller support, all the supports are roller supports. And as you can see, in this particular scenario, roller support is providing only vertical restriction, so no horizontal restriction is there. So if we apply load in this direction, if we apply load at this joint like this, the whole structure will move from this particular point to in this direction. Whole structure will move in this direction. So and it cannot show any restraint against this movement. So ultimately, uh, our main consideration, we actually, why we build structure, we build structure so that it can take some certain amount of load, is it can resist certain amount of load. But if our structure become unstable even for a very small amount of load, then there is no application of this kind of structure. So before going to the analysis, we must understand that the whatever the structure is, it should be stable enough to resist some sorts of loads for which it is designed for. Clear? Now the truss are externally unstable. The truss are externally unstable since the support reaction have lines of action. Support reaction have lines of action that are either concurrent or parallel. Clear? The support reaction, these are the one support reaction, this is one support reaction, this is one support reaction. In this particular case, all the support reaction are concurrent in nature because they are all are passing through one particular point, that is this particular joint. So when the trusses are externally unstable, since the support reactions have lines of action that are concurrent. In this scenario, the support reaction have lines of reaction that are parallel. So in both of the cases, our structure will become unstable. Now we will discuss about method of joint. Why we actually use method of joint? Just first let me remove these things. We use method of joints. There are two particular, basically there is two methods within your syllabus. One is method of joints and one is method of section. We will use these two method, but these two methods to analyze our truss structure. That is, we will using these two particular method of joints and method of section, we will find out what are the member forces that member forces are there within each member of the truss structure. So what actually the method of joint is. So there are I have told you that to determine the member forces, we use this method of joints. And what are the steps through which we can find out the member forces? And these are the steps. As you can see, the first step is draw the free body diagram of the truss. This is very important in structural analysis. In any kind of structural analysis, drawing the free body diagram is very important. In all the cases, you have to do this free or draw the free body diagram, whatever it may be. But in everywhere, if you are going to analyze the structure, drawing the free body diagram is very important. So you have to keep in mind. So you have to keep in mind these things, that drawing the free body diagram is very important. And how to draw the free body diagram, you already have learned in the engineering mechanics courses. So where there is some restriction against at the support, in order to in order, as you are providing some restriction, there will be some support reaction, because as per Newton's third law, each action have an equal and opposite reaction. So when you are providing a restriction, there will be some sorts of reactive forces that will be acting within the that particular support or that particular joint, whatever uh, the cases may be. So in this particular, just if we take this particular structure, this is one structure. At this particular point, we have a hinged joint, and at this point we have a rocker joint. So at hinged joint, actually what actual hinged joint do, it actually restrict vertical and as well as horizontal movement. So as it restrict vertical and horizontal movement, as it restrict horizontal and vertical and horizontal movement, so uh, there will be two sorts of reaction. One is in the vertical direction, like this, and one will be horizontal reaction. One horizontal reaction will be there. And as this is a rocker joint, so it is allowing movement in the horizontal direction. So there will be only vertical reaction, because it is creating restraint against the vertical movement only. So there will be only vertical reaction. But as we can see that in this particular structure, our loads are only vertical. There is only one vertical load, so there is no horizontal load. So when we apply sum of fx equals to 0, that is sum of all the horizontal forces equals to 0, you can see from this particular figure that other than these reactive forces at A, horizontal reactive forces at A, there is no other vertical forces. Is there any? No, there is no other vertical, sorry, there is no other horizontal forces other than these particular forces. So as there is no other vertical horizontal forces, so ultimately this force will become zero. And as this is becoming zero, so that's why our free body diagram will look like this one. That is R1, that is one vertical reaction at point joint A. R2, that is the vertical reaction at joint D, and L is the applied external load. So this is the free body diagram of this particular truss, plain truss. Now after the free body diagram is drawn, what we need to know, we need to solve for the reactive forces. What are the reactive forces are? So we know how to solve the reactive forces. We already have done this kind of problem. We have already have solved this kind of problem in our engineering mechanics courses, and we have done lots of problems on this. But still I am going to discuss about a little bit about this, because uh, for the time being, you have to know, even if you forgot that, you have to know how to do that. So first of all, determine external reactions by applying equilibrium equations to the whole truss. So uh, this is the basics of finding out the unknown reactive forces. So what we have to do, we have to apply equilibrium equations. What are the equilibrium equations? The equilibrium equations are sum of fx equals to 0, sum of fx equals to 0, sum of fx equals to 0. Another one is sum of fy equals to 0, and sum of moment equals to 0. So these are the three equilibrium equations. Sum of fx equals to 0, that is sum of all the horizontal forces equals to 0. Sum of moment equals to 0, that is sum of all the moment equals to 0. And sum of fy, that is sum of all the vertical forces, will be equals to 0. So just applying this, we can easily find out what are the reactive forces are. Now after this one is done, we have to perform the force analysis of the remainder of the truss by method of joints. Now, once the unknown reactive forces are computed, what are the unknown reactive forces, then we need to compute what are the member forces within the structure. And we will perform the force analysis of the remainder of the truss by method of joints. Just let me erase all these things. No, first start with any joint. How to do the analysis of method of joint? uh, Before I have already discussed that while just going through the stable structural determinate or structural statically indeterminate structure, while discussing about the statically determinate and statically indeterminate structure, we have discussed that uh, our available equilibrium equations we have is 2j, that is number of joint into 2, and at each joint we have two equilibrium equations, that is sum of fx equals to 0 and sum of fy equals to 0. And in this particular solution method, that is method of joints, we will use that particular equilibrium equations to solve for the unknown member forces. So as we if we take out joint a, suppose this is joint a, we have just taken it out at this particular figure. Let's just see, we have taken out joint a and just drawn the free body diagram of joint a. So what's there? one reactive force R1 is there. And as we have cutted a member, because we have just drawn this joint, so the member will, we have to cut this member. So as we are cutting this member, so we have to consider the member forces due to this particular in this section, because there were some sorts of forces as we are cutting it. So there will be some member forces. Suppose this is AF, that is member force AF, and we need to find out what the member force AF is. And at the same time, at this particular for this particular member, well, there will be also one member forces, that is AB, that is force AB, suppose. Now let us assume that this member force is compressive and this member force is tensile in nature. So as the compression and tensile configuration is concerned, you can see for the case of compression it will undergo this kind of forces. And for that we denote it like this. When the arrow is coming towards our joint, that is denoted by, that means that we are considering that kind of forces as compressive force. And when the arrow is going uh, against our joint, in that case you can see the configuration is tensile configuration. So this is the free body diagram of joint A. Now we will apply the equilibrium equations, that is sum of fx equals to 0 and sum of fy equals to 0. In here, if we apply the equilibrium equation, we can easily find out what is the unknown member forces are there, because R1 we have already determined, computed what is the value of reaction forces are. So we have only two unknowns, AF and member force AF and member force AB. So two unknowns, and we have two available equilibrium equations. One is sum of fx equals to 0 and another one is sum of fy equals to 0. So using that two particular equations, we can easily find out the two unknown member forces AF and AB. But before starting with any points, we have chosen joint A. Someone may say that no, I will choose this particular joint first, not A. So there is some logic why I am choosing this particular joint, because as you can see that we have only two available equilibrium equations at one particular joint, that is sum of fx is 0 and sum of fy is 0. So if we consider this particular joint, what will happen? We have one member force, this one. We have two member and second member force in this direction. We have third member force in this direction. All the member forces is unknown to me. So we have three unknown member forces, but the available equilibrium equations is only two. So using that two particular equilibrium equations, sum of fx equals to 0 and sum of fy equals to 0, we cannot solve for this particular joint. We cannot solve for all the three member forces, because the available equilibrium equations is inadequate. Sorry, available equilibrium equations is inadequate. So that's why we have to consider, we have to start with one such joint where the unknown member forces is not more than 2, or unknown forces is not more than 2. So there should be maximum of two member unknown forces. So we will start with that joint first. Now once you have started from this joint, what will happen? As you can see, tension indicated by an arrow away from the pin and compression indicated by an arrow towards the pin. I have already discussed about this. Now magnitude of AF, we can find out the magnitude of AF from sum of Fy equals to 0. If we apply sum of Fy equals to 0, uh, if this angle is theta, so vertical component will be AF sine theta, and that will be equals to R1. So AF sine theta equals to R1, so AF is equals to R1 divided by sine theta, and the value will be our unknown member forces. That will be the value of unknown member forces F. And if we consider sum of fx equals to 0, then as we have already found out what is the value of AF, so uh, a, a, AB, member force AB plus member force AF cos theta will be equals to 0. So ultimately we will from now, as the value of AF is known, from there we can easily find out the value of AB as well. So these two member forces are now known to us. So this member force is known now, this member force is known now. Now if we go to this particular joint, this member forces is known to me already. Now now we have only two unknown member forces at this particular joint. One is this member force, another is this member force. So if we take out this particular joint now, if we take out this particular joint now, we can easily solve for that, solve for the unknown member forces. Clear? So this is known. Let me remove this one first. You can see this is known now. Now this is unknown, this member force is unknown. We are considering joint F, we are considering joint F. So as there is two unknown only, if we apply sum of fx equals to 0 and sum of fy equals to 0, we can easily solve for the whole thing, that is member force EF and member force BF. We can easily solve for that. Now once this one is solved, so now we know this member force, this member force, this member force, and this member force. Now if we go to joint B, that is at this particular joint, so this is known, this is known, and this is external loading, that is also known to me. So now we have one unknown member forces, two unknown member forces. So we can go through the point B. Now we will consider joint B and draw the free body diagram of joint B. And again we will follow the same rules, that is sum of fx equals to 0, one equilibrium equation, and second equilibrium equation is sum of fy equals to 0. And if we mm, do that, we can easily find out what is the value of member force BE and member force BC. Now once this is done, so now member force BC, this one is known to me, this one is also known to me, this one was previously we have computed. Now if we consider joint E, we have one and two unknown member forces. Even if we consider joint C, we have one and two unknown member forces. So we can go through any point, we can choose C as well as we can choose C. That depends on you, whether what is the particular point you are going to choose. So if we consider joint E, this will be the free body diagram, this is known, this is sorry, at this particular point we have considered joint C first. So as if we take out the joint C, if you draw the free body diagram of joint C, so what will happen? This is one member force, this is the known member force, and as you can see the and this is the member force CE. Now if we apply sum of fx equals to 0, so what will happen, as these two are opposite in direction, and the member sum of member force must be 0, so ultimately obviously these two member forces should be equal, that is member force BC and member force CD will should be equal, because member force CE lies at an angle 90 degree with both this particular line. So there will be no contribution of member force CE in horizontal direction. So ultimately member force BC will be equals to member force CD, and there, as there is no other horizontal forces, there is there is no other vertical forces, as there is no other vertical forces, so ultimately if we apply sum of Fy equals to 0, this member force CE will ultimately become 0. Now as CE is has gone become 0, now if we consider this particular joint E, so as you can see, this member force is 0. So while drawing the free body diagram, we can remove this one, because the member force as this particular member is 0. So if we draw now, this is known, this is also known, and this is only one unknown. So there is only one unknown, you can easily solve for it just by applying equilibrium equations. And once this is done, you can go to joint D. But as you can see, all the forces is now known to you, this one before going to joint D, we can see the all the member forces is known to us. Now we will draw the free body diagram and solve for it, and we will just justify whether our calculations were right or whether our calculations was wrong. For that we have to do the last one. Otherwise if our calculations is everything good, then from this particular up to step 5 we can easily say that what are the member forces are. And one more thing, important thing is that suppose at any point if the member force is 0, we call that member as zero force member. If the member force is 0, we call that member as zero force member. That is very important term. And you can find out mm, in many competitive exams that you uh, in question papers you will be asked to find out the zero force members. What are the zero force members? So you have to do that. Now one more important thing, that suppose while we are considering any force, if we are considering forces as tensile in nature, this kind of configuration, when the forces are going away from the joint, this kind of forces we call tensile force. Now if we consider tensile force in nature, and after calculating everything, if the value comes out to be a negative one, then we from that particular value we can say that as the value is negative, so the ultimate actual force was compressive in nature. Clear? So if you consider tensile force tensile in nature, and taking the tensile direction as your base direction, if you compute everything, and if the value comes out to be a negative value, then our actual structure is undergoing actually in the actual structure the member is undergoing compression. We have to understand this one. And if we consider any compressive, suppose if we consider any compressive force, we suppose we are considering this force to be a compressive force, but after calculation this force comes out to be minus 5 kilonewton or minus 10 kilonewton, then ultimately actually in our real life structure, the member, this particular member is undergoing tension. That is one important thing you have to understand. And after solving for all the member forces, we can easily solve if taking tensile value, if the value is coming out to be positive, then the member is undergoing tensile forces. And if taking the compressive forces, if the member is undergoing compression, then it is compressive forces. And if the value is coming negative, then it will be the opposite forces. And we just show the tensile and compressive forces like this one when the arrow is going against the member, that is the tensile forces. When the arrow is coming towards the member, this one is compressive forces. So after calculating everything, we have to show the member for show whether this member is under tension or compression, like this one. We have to draw a arrow, and within just with this we can just make a diagram that this particular member is undergoing tension, and this particular member is undergoing compression. This particular member is undergoing compression. This particular member is undergoing compression. This particular member is this particular member is undergoing tension. This particular member is undergoing compression, and like this one. For every member we can just say this member is undergoing tension or compression, and simultaneously we can write down the value here in at the above of every uh, single member. Clear? Now we will stop here today. In the next lecture we will discuss about uh, one particular problems of we will discuss about we will solve actually one problems using method of joints. Thank you.